Hello students, this recording is on factoring trinomials, and I have a little bit of a unique method in factoring trinomials, different from maybe something you've seen in textbooks. So let's start with a trinomial. Let's use the trinomial 3x squared plus 14x plus 8. Now in this method of factoring, it will factor into two binomials, but we're going to just start with a term of x in each of these binomials. Then we're going to form a fraction taking into effect the leading coefficient of 3. So we're going to put fractions in each of these binomials, letting the denominator be 3. Now what we do is we take the product of the leading coefficient and the constant 8 on the end. 3 times 8 is 24. Then we look at this center coefficient, which is 14. The goal is to list all of the factors of 24 until we get a set that will add or be a sum of 14. Well, one such factor is 1 times 24, but 1 plus 24 is not 14. Another is 2 and 12. Another would be 3 and 8. You could do 4 times 6, and this could continue, but very quickly we see that the 2 and 12 combination, 2 plus 12 is 14, so that's the combination we want. What we do is we put the 2 over one of the 3's and the 12 over the other. Since both of these are plus a positive 2 and a positive 12, we're going to use plus signs in these binomials. Now we note on the second binomial that that fraction can reduce down into a whole number. 12 thirds is 4. So now the last step is when you have a fraction still here rather than a whole number, you're going to move the denominator up as the coefficient of the x term, and then this will give you the factorization of your trinomial. Alright, let's try another one. Suppose we have the trinomial 2x squared plus 13x plus 18. We're going to do the same process. Two binomials, give them only the x variable. The leading coefficient is a 2, so I'm going to put a couple of fractions here where the denominators are 2's. Build a table. Take the product of the leading coefficient and the 18. 2 times 18 is 36. And then your middle coefficient is a 13. So we're going to list factors of 36 and look for the set that will give me a sum of 13. 1 and 36 is not going to work. 2 and 18 is not going to work. 3 and 12, 4 and 9, here it is. 4 times 9 is 36, and 4 plus 9 is 13. Well, it's a positive 4, so I put plus 4 halves, and a positive 9, so a plus 9 halves. The first binomial, the 4 halves can drop down into a whole number as 2. But the second binomial does not have a whole number, so I leave the first binomial alone. But on the second binomial, I pull a 2 up as a coefficient of my x, and this is my factorization. Right? One more example. Suppose I go ahead and do one that has a leading coefficient of 1. Will this work also using this process? Let's try it. An x and an x. And your leading coefficient is 1, so if I really stick with the process, that means a fraction with a denominator of 1. I build a table. 1 times 10 is 10, and the middle coefficient is 7. List factors of 10 until I get a set that will multiply to be 10 and add to be 7, which is 2 and 5. So it's a positive 2 and a positive 5, which results in an x plus 2 times an x plus 5, and it is factored. Now I did say that would be my last example, but I think I'll do one more, going back to the leading coefficient, not 1. Suppose we have 6x squared minus 7x minus 5. Same process. Two binomials with leading terms of x's. Your leading coefficient is 6, so we create these fractions with denominators of 6. Build the table. 6 times a negative 5 is a negative 30, and your middle coefficient is a negative 7. List factorizations. 1 times negative 30, 2 times negative 15, 3 times negative 10, this will be the combination, 3 and negative 10, that add to be the negative 7. So it's a positive 3 and a negative 10. Both of these fractions can be simplified, x plus a half, and then x minus 5/3. So I bring the 2 up in front of the x in the first binomial, and the 3 up in front of the x in the second binomial, and it is factored. So again, this is a different way of factoring trinomials. I think it's pretty quick and easy, and I hope that you found this to be an option that maybe you'll use in the future.